Welcome to the last video of this series, cracking paper 2 of the Cambridge iGCSE exam in chemistry. And we've got 10 more questions to break down for you. I'm going to use everything that I have learned as a GCSE examiner to help support you with a few shortcuts and maybe give you a little bit of understanding as to what the examiner is actually looking for. And in addition to that, we've also got the results from 50 Year 11s that answered these questions, and we'll be looking at those results and seeing which questions were the trickiest ones, as well as looking at the questions that I found very, very easy. So let's make a start with question number 31. There are 3 other videos in the series, so do feel free to skip back to those videos and watch those first, but we can go into this one, no problem at all. Pause the video if you would like to have a go at the question right now. Okay, so this question is actually arguably the most difficult question that we have in the entire series. So we're going to start off with this one. It's a simple one-line question, just asking how many silicon atoms are bonded to each oxygen atom in a crystal of silicon 4 oxide. And there's 4 answers. It's 1, 2, 3, and 4. Now, the most popular answer was actually answer D, response D, which was 4. And out of the cohort that we actually had, half the students actually picked it, over half, which actually 55 students picked that one as their answer. In actual fact, this answer is terribly, terribly incorrect. So what we're going to do is we're going to have a look at silicon 4 oxide, and silicon 4 oxide is actually is actually sand. It's actually got a structure that is very much similar to. It's very similar to the structures that you actually find in diamond and also in ice. So the silicon itself has 4 bonds around it, and what you find is that in between each of these arms, I should have that as a straight line. I want to be able to show you that correctly. Here we go. Between each of the silicon atoms is an oxygen. So I'm going to do an oxygen here. There we go. So this is, so you can imagine that each of the silicons is in contact with 4 over here. Now, if you were to look at the question and think, right, okay, I've read the question, silicon atoms bonded to oxygen atoms, crystal of silicon 4 oxide. This question must be about that oxidation state, which is 4. And that is pretty much what people thought. People thought that this question was all about count how many times silicon is bonded onto oxygen. And that would be the natural choice, 4. However, the question does not ask that. The question asks how many silicon atoms are bonded to each oxygen atom. So what you have to look at is you have to look at an oxygen atom. And the oxygen atoms are bonded onto 2 silicon atoms. So the correct answer is B, 2. Only 33% of the students surveyed actually got that correct. I believe that the inclusion of the Roman numeral 4 here is pretty much what locked in what students would be choosing, but it just goes to show that you must be very, very careful. These two are points where you can quickly dismiss those because silicon is joined onto 4 oxygen, and each oxygen is joined onto silicon. So those are your points where you can actually exclude those. It's either 2 or 4, and the correct answer is 2. So we're going to move on to the next question. Pause the video if you wish to have a guess at this video. So what we have over here is a question just about combustion again. We've actually already spoken to each other about combustion in the sense that we actually had incomplete combustion in the previous video from the series, and one of the questions was actually asking about carbon monoxide. So it's actually a fairly common theme. You can expect to have combustion somewhere in the paper itself. This equation represents the incomplete combustion. So I've just already mentioned that carbon monoxide is what we're looking for, so we can exclude that and that. The answer is either A or C. So key to this is making sure that you actually count the right numbers of carbons. So 3 times 2 is 6, so there's no extra clues there. You've got 8 times 2 equals 16 hydrogens in each of those. 16 hydrogens, and water is the only other product that's coming from these chemical reactions. So 16 divided by 2 is 8, and is not 16. Times 2 equals 32. That would mean that 32 hydrogens are on the left-hand side. So it's a nice little twisty question, little twist to see whether you can actually count the number of hydrogens on either side. So having seen that, choice C is very much the incorrect choice. The answer is choice A. Half the cohort actually got that. Choice C, funnily enough, was actually the least popular choice. Choice B was the most popular mistake to make. About 41% of our cohort looked at that and perhaps chose that because each of these had water, so they automatically thought, right, okay, this is a question on complete combustion, not incomplete combustion. So always check very, very carefully, to see if the question is asking you about complete combustion. If it is, then you need to give carbon dioxide, and if it's not, it's carbon monoxide. So let's look at the next question now. Pause the video if you'd like to have a go at it yourself right now. So for this question, the majority actually got this right, but only half the students surveyed in our cohort actually secured the right answer. And what it basically comes down to is knowing what actually happens in a fractionating column or a fractionating tower with crude oil. So it's essentially the material where you have heated crude oil going into the tower, and then at various points, as you rise above the fractionating tower, the temperature decreases. So it's cool up here, and it's hotter down here. And at the points where the fractions actually have their boiling points, the gases, the vapors, will turn to liquids. So the right answer for this has to be obtained by knowing that ship fuel comes from fuel oil, which is a fraction, and naphtha comes, which is one of the fractions as well, is used to make chemicals. It's actually a precursor for many synthetic materials, pharmaceuticals, medicines, and so on and so forth, plastics too, and polymers. So naphtha, making chemicals, it was just basically a question where if you have revised it and you've learnt the uses of the fractions, then you secure the answer. Interestingly enough, B and D were the least popular answers. I think that's because everyone seems to remember that bitumen is used for making roads, so that was the easiest one to exclude. Right. So make sure that you know about naphtha, kerosene. Make sure you know about octane. Make sure you know about diesel before you go into your exam. Question 34. You've got a chance to pause the video if you wish to have a go at that question. So it's a familiar format, and I've already mentioned it in the series. All you need to do is read the question. Don't look at the choices, and don't be swayed by the choices. Don't be scared of thinking that you'll get to a conclusion and the choices aren't there. It's best to really think it through rather than try and extract clues, because there are 3 confusing answers and one truth. So X, Y, and Z are 3 hydrocarbons, and what do they all have in common? Now, 82% of our cohort actually scored the right answer, so it's a question that you do need to get right. The 18% that got it wrong were evenly distributing their answers between A, C, and D. So 82% knew the answer, and I can conclude that the rest will just guess randomly at the others. What do they have in common? Well, are they all alkenes? The answer for part 1 is a resounding yes. They are all alkenes. So what do they have in common? They are all alkenes. We need to be able to see which choice we can exclude straight away. They are all part of the same homologous series. Now, are they differing in a sense that if you have one of the hydrogens in X replaced by a CH3, is that true? Well, the answer is yes. So they're definitely the same homologous series. Now, if we replaced that hydrogen with a CH3, would we get Z? The answer is yes. So they are all part of the same homologous series. And part 3, do they all have the same boiling point? I'm afraid to say that that is not true, because the longer the molecule, the higher the boiling point. Okay, and so that's a trend that you need to be aware of. It all originates from having more atoms. If you have more atoms, you have more electrons in the molecules that are present, and electrons give rise to electrostatic forces between the molecules. That's what bonds them, bonds different molecules together. But these electrostatic attractive forces are very short distance, and they're very easily overcome. So the correct answer is B. Now let's move on to the next question, question number 35. We're nearly there for the series. Which list shows the fractions obtained from distilling petroleum in order of increasing boiling point? So if you want to pause the video and have a go at this question, you may do so. Okay, so it's in terms of increasing boiling point, and the fact that bitumen is actually indicated as being an early one for A excludes A completely. That was actually the least popular answer. Unfortunately, bitumen is not present in B, C, or D, so we can't rely upon bitumen being something that will help us any further. You've got diesel oil, then gasoline, and naphtha, then kerosene in the second one. You've got gasoline, naphtha, and kerosene, and diesel oil. So those two are very, very similar to each other in terms of the order. And then you've got kerosene, lubricating oil, naphtha, and refinery gas. Now, refinery gas may actually be tempting to select particularly if you were not aware of the order of the other fractions going from the top of the fractionating tower to the bottom. But in actual fact, kerosene, lubricating oil, and naphtha are not in the right order, and nor is diesel oil, gasoline, naphtha, and kerosene. The correct order is gasoline, naphtha, kerosene, and diesel oil, because you're going from the one with the lowest boiling point to the highest boiling point as given in the question. So gasoline has a fairly low boiling point. It's petrol. Petrols always seem to have lower boiling points than diesel, which is why this one is wrong. And we've also got naphtha, which is in the wrong place as well. So naphtha should be in a position where it is stated before kerosene, and it's wrong here. And we've also got kerosene here, which is after gasoline, which is absolutely fine. But diesel oil is actually the heaviest one. It's actually the one with the longest molecule. We could actually maybe think of that as being very oily and very thick, and that may actually help you remember the order. So do what you need to do in order to remember the order of all of the fractions down the fractionating tower. There will always be one question that you can expect that will reward you for that fact. I'm going to move on to question number 36. So have a look at that and pause the video if you would wish to attempt that question. So 62% of the students surveyed in our cohort actually got this right. The most popular mistake was almost 20% going for D. So D was actually the most popular mistake to make. The statement about sulfur or one of its compounds is correct. So this is all to do with revising sulfur and the uses of sulfur. Does it occur naturally as the element sulfur? Well, yes, it does. Is sulfur dioxide used to kill bacteria in drinking water? No, it's actually chlorine that is used. Sulfuric acid is a weak acid. Well, that's a definite no. That was the least popular answer. That is actually a strong acid. Dilute sulfuric acid is a dehydrating agent? No, that is not correct. It's actually concentrated sulfuric acid that can be used as a dehydrating agent. So a couple of facts about the uses of sulfur should be able to secure you a mark. I'm going to go on to question number 37 in our series. Pause the video if you wish to have a go at that. So almost 60% of those surveyed got this one correct, and the percentages for the other three answers were 14, 16, and 10%. So you either knew your oxidation, reduction chemistry well, or you would have to be forced to take a guess. This is an example of a redox reaction. So the zinc itself is an atom, and it becomes a 2+ ion. So this will lose 2 electrons. So each zinc atom will lose 2 electrons each. Copper 2 ion, will actually gain 2 electrons to become the copper atom, because it's a positive charge and you're adding something that's negatively charged, which is possible. So that's basically explaining what that reaction, what's happening is that reaction. Which statement about the reaction is correct? So now what you need to do is you need to be able to connect it with these two terms, oxidizing agent and reducing agent. So an oxidizing agent oxidizes something else. Okay, and a reducing agent reduces something else. You just say that to yourself, eventually you find that you remember it and you'll be able to recall it at the right time. So an oxidizing agent oxidizes something else, a reducing agent reduces something else. So now what you need to do is you need to connect it. It is also worth learning that an oxidizing agent is reduced itself. And if you learn that extra fact, the reducing agent is always going to be doing the opposite. It's actually oxidized itself. So if you learn that extra fact, then you face a question like this, it's very, very easy. Reduction is gain in electrons, so it would be gaining electrons, and oxidation is a loss of electrons. So that's a loss, that's a gain. And now we can connect it. The copper gains electrons, so it is the oxidizing agent. The zinc loses electrons, so it is the reducing agent. So the reducing agent there excludes B and A as an answer. The copper oxidizes something else, so it is actually reduced itself, and the correct answer for that then becomes D. So D is the right answer. Think about it through logic, and you should be able to get the answer that they desire. I'm going to go on to question 38. We're nearly there for the series. We've got this question and two more afterwards, so pause the video and have a go at the question if you need to. So this statement is asking you to identify the imposter statement. Which one is not correct? An ion catalyst is used to increase the rate of reaction in the Haber process, as that is not the choice to make. The reaction is reversible. The reaction is carried out at a high temperature to increase the rate of reaction. Has some truth to it, because you don't want to lower the temperature during the Haber process. Not enough particles will actually have sufficient energy to overcome the activation energy barriers that they need to in order to react. So that's a more difficult that's a difficult truth to extract from the question. But it then leaves C as the choice to make. The reaction is carried out at low pressure to increase the yield of ammonia. If we imagine the hydrogen as 3 volumes and the nitrogen as 1 volume, the ammonia as 2 volumes, if you decrease, you will actually find that the backwards reaction rises in number in order to remove the constraint of low pressure. It actually produces more volumes of gas, and that is in accordance to the Chatelier's principle as well. You don't need to justify it. All you need to do is just give the right conclusion. Almost there. We've got question 39 now. Pause the video if you would like to have a go at it. So we've actually got less success with this one than the previous one. In the previous one, only 60% of the cohort survey got it right. And in this question, less than half, 49%, actually got this one right. One step in the manufacture of sulfuric acid is the oxidation of sulfur dioxide to sulfur trioxide. What conditions are used for this step? The key to this question is understanding this part over here where you've got the pressure in terms of atmospheres. The temperature is actually kept the same, which is very, very generous, I must say. No one actually picked in the cohort that we tested, no one actually picked iron, because I believe that they realized that iron is a catalyst that's known for the Haber process. So we can get rid of those ones straight away. Vanadium 5 oxide is definitely the catalyst to go for. So it's either between B and D. So it's all about pressure. And it just so happens that the correct answer is B. we actually keep the pressure at 1.5 atmospheres. So the correct answer is B. The most popular mistake was actually D. People actually thought that 200 atmospheres was the right answer, but unfortunately it was not. And we can actually justify that by taking a look at the equation. Two SO2 plus O2 goes to 2SO3 as the forward reaction. It's a reversible reaction. You've actually got 3 volumes on this side, and you've got 2 volumes of gas on this side. So if you increase the pressure, what would actually happen is that would drive towards the right-hand side. But the reality of the situation is that you actually keep it at 1.5 atmospheres because you don't necessarily get too much of an advantage by raising the pressure. It's a very, very subtle point, but when you revise it, you've got to make sure that you revise the fact that the pressure, even though it would actually drive the reaction forward, the reality of the situation is that you only use pressure of 1.5 atmospheres. So B is the right choice to make. And finally, question 40. So pause the video if you would like to have a go at it. So which changes represent reduction? Remember, reduction is a change where you have a gain in electrons from atoms, or ions. So definitely choice 1. We can exclude choice D as an answer. Now this is Mn7, and that would be the manganese 7 plus, going to effectively the manganese 2 plus. You could just think of that, but the reality of the situation is that you would actually have that in existence in an ion that is that would be potassium manganate, or potassium manganate 7. So definitely you can actually see that would actually be a plus 7 state. That would be a plus 2 state. You have to add 5 negative electrons. So it's like adding 5 of these, and you get to Mn2. So that was definitely a choice as well. That does represent reduction. And then finally, you've got sulfate 4. So the sulfur is actually a plus here. So it's a plus 4. And then sulfate plus 6. That is not reduction. That is actually an oxidation, because you would actually have to add you would actually have to remove electrons rather, and it's by removing electrons. Just make that very clear over here. You'd have to add that. You'd have to take away, and then take away something else, which is negative. That is clearly not the right answer, and that then leads you to A, and A is the correct response. Less than half of the cohort actually got that right, so it is a difficult question, especially with the sulfate, but B was the most popular answer that caused the biggest errors. Almost 40% actually got B, so the top candidates will actually get that. A nice, if I come back to this point, a nice little shortcut, strictly not true, but you might want to imagine that Mn7 plus exists in MnO4. Remember that oxidation numbers is kind of like a fictitious model. We just use it to try and justify what the electrons are doing if complete ionicity did actually exist in substances. The good news is that you don't have to go into it with that much depth in order to justify oxidation numbers. That's not part of your spec. Brings us to the end, so thank you very much for watching, and I hope that these have been useful. Leave a like, and for keeping up to date with all the videos that we do, please make sure that you leave us a subscribe. Thank you very much for joining us, and best of luck with your exams.